Alright, so the difference between recursive and iterative. The iterative is doing the same thing. It keeps advancing to the next node and checking if it has the value or if we've reached the end of the list. And then the recursive one is doing the same thing, just with a recursive call at the end. So you can see all the same logic between these two. And this is one case, maybe it's debatable, but I would argue that the iterative version is a little bit cleaner, a little easier to read, a little easier to understand. Again, debatable. You might like the iterative version more. But I prefer the recursive version because I'm thinking more, it's kind of likened to the state pattern where I'm thinking, okay, I have these three different situations that I can have. What do I have to do with each situation? And I can reason about these a lot simpler, where with the iterative version, I'm thinking about all the overhead. I have to worry about tracking which node I'm looking at currently. I have to really think about the whole structure of the entire algorithm. With the recursive one, I'm saying, okay, there's three situations that can happen. I'm looking at the last node of the list. Sorry, let me back up a bit. There's three different things. Either I'm looking at a node that contains the element I'm looking for. I'm looking at a node that doesn't contain the element I'm looking for and it's the end of the list. Or I'm looking at a node that doesn't contain the element I'm looking for and it's not the end of the list. There's three different situations that can happen that are collectively exhaustive. Let me put those in an if block and just say, what do I do in each of these situations? And then I can write, okay, if I found it, just return this node. If I didn't find it and I'm at the end, return null. If I didn't find it and I'm not at the end, make the recursive call and punt the problem down the list to the next node. With the find iterative, it's a little bit tougher to see this at a glance, but if we read it, if we digest the code and look through it all, we can understand, okay, we're iterating through the entire list and asking each node the same question, do you have to find? So it's debatable. I like the recursive one a little better, but the preference is up to you. This is where we're starting to see that we can take that structure of recursion and use it a little bit to our advantage. I didn't add any more text here, but Foreach, there's really not much to say. I don't know, I was stumped on even a second bullet point to talk about others. But Foreach, we saw this in my code a little bit when I gave examples in lecture. So let's talk about this directly. For each, if I have a data structure and I do .foreach on it, it's calling a function on every single node in this, for linked list anyway, every single node of the linked list or every element of the data structure. So when I call for each on something, I give it a function, and it's going to call that function on every single element of the list. I'm not concerned with the return type or the return value when I call for each. I just want for each call, that function called on everything. So we would use for each often when we are concerned with the side effects of our function call. So for example, we want to print everything to the screen. We would say for each print line, and then just print all the stuff to the screen. We're worried about the side effect of printing values to the screen and showing them to the user. Or maybe we have objects, references to objects, and we want to call a method with a side effect. Maybe we want to call purchase equipment in Clicker or something like that. We want to call purchase on each type of equipment to buy one of each type. Maybe that's something we want to do. We would say for each purchase this, and then have that called on every single type. So to do that, we'll call the function on the current node, the node that this is called on, and then as long as we're not at the end of the list, make the recursive call. We're just going to call the function on the next node, which will make the recursive call next. Yeah.
If A is in any rough, does that mean you can make changes to it since it's mutable?
A is in any ref, you make changes because it's mutable. Yes. Yeah, so if you have some custom class, like I don't have a good example off the top of my head, but if you write some class and you have some mutable state in that class, and that's your value for A, you have some linked lists of that type, you can call a method with side effects and mutate the state of those instances, of those any refs, yes. And that's why you would want to call it for each. You're concerned about the side effects. You would never call this, since it returns unit, you would never call this if you don't have some side effects. So it is more of an OOP style of method because you only call it for the side effects. As opposed, I haven't talked about that much, but as opposed to a functional programming, in functional programming, which we don't really talk about much in this class, we talk about first order functions, this idea of passing functions. But what that's leading to, if you take CSC 305, you talk about this a lot more. Functional programming is programming without any mutable state at all. So if we don't have any mutable state, which functional programming pretty much says no mutable state, and then gets things done like that, you wouldn't really call it for each because you're only concerned with the mutable stateness and side effects. But that's a whole different conversation. I don't know if we have time to stuff that into this course. All right. Map. I think I used this once or twice in code that I showed, just flash real quick on the screen. Kind of to foreshadow these next few slides. Map is when you want to call a function on a data structure and return a whole new data structure based on the return values of that function call. So if I want to apply some function to every single element of my list and return a whole new list, I would call .map with that function on the head of my list. So this is going to compute a new value, take the value at the node I'm looking at, create a new value with that, and if I'm at the end of the list, create a new node that points to null. If I'm not at the end of the list, I'm going to create a new node with that new value that points to a recursive call on the next node of the list of map with that same function. So this is calling this on the head is going to return a new list that is that entire list with that function applied to every single node. A brand new list with that function applied to every single node. So for example, if I have some list, just the numbers, integers, 1 to 10, and I would like a new list with all those numbers squared for whatever reason. I don't know why I'd want to do that, I just feel like it. So if I want to do this, I'm going to call my map function, and it's the same syntax for the linked list node that we're using in class, that we're building in class. I'll call this, give it a function that takes an int and returns the input squared. And now I have numbers squared, which is every single number in the original list, a brand new list with every single number but the square value of that number. So if I want to change an entire list, where before we would create an empty list, iterate over our list, and for each element append to the end of that list a new value with the function applied. That's how we would do it with iteration. Here, if we just call .map and say give it a function, give me a new list, it's going to do all that for us. Yeah.
For the map function, you know how you hash the type as A in the other function?
Yeah.
Can you use that for the int here and map input? Can you just make it type?
Yes. So in the previous slide, we're looking at the code for this, and I'm kind of omitting it, but this is inside the linked list class, and linked list itself takes the type parameter A. So I'll have a linked list node of type A, and then when I call this function, A is already determined by the type that was given when I created that linked list. The same thing is happening here. When I create the list in Scala, I'm telling it its type is int. So now when I call .map, the type is going to be int for that. Which the next slide, there's actually a little bit more to this one. We'll see on the next slide. So when I give this function, this has to take in an int because that's the type of my list. If this doesn't match this, if these types don't match, I'm going to get an error there.
Can there be like multiple types in this?
Yes, so that's my next one. So we can actually have multiple types. So we don't always want to just take the type and return a new list of that same type. Sometimes we want to change the entire type of the list. So say I want, say I have a list of ints, and I want to, such a dumb example, but this is what popped in my head. So I have a list of ints, and I want to figure out which, for each int, I want to figure out the percentage that int contributes to the total of that list. Say I want to do something like that. I would take in ints. I have a list of ints, and I want to return a list of doubles, something with some floating point values. I might want to change the type. So the map, so the Scala built-in list does it this way. Map itself takes a type parameter. So we have A is the type parameter of the list itself. So if I have a list of ints, A is going to be int already. That's already determined before I call map. But when I call map, I can have a second type parameter, which is the type that I'm returning, and then give it a function from A to B and return a new linked list of type B. So if I want to do that, I can have another type parameter here and change the types as I call map. And thanks to Scala's type inference, if I give this a function, say A is int, if I give this a function that takes in an int and returns any other type, it will infer that type, and I don't have to specify that type parameter B when I call map. So like the Scala built-in map does take another type parameter, but I don't have to specify it here. It just sees that I'm returning ints here, and it infers that that type parameter is int. But I can change the types by using two type parameters like this. Yeah.
So what is the type you have all A's? You're not expecting a specific type. So if you have all A's here, is it work or not?
So if we have all A's here, like we did in the previous slide, A is going to be the type when we created the list. So when we create a linked list node and give it a type for its value, A is going to be that value. So like, when we create a linked list node, we have this type parameter here, which is based on the values that we give it, that we start with. And then every function, these functions don't take type parameters, or these methods don't take type parameters. They just borrow that A, the type of the list itself, or the list node in this case itself. And then when we get to map, this is the only one that needs a second type. So then the map method itself takes that second type parameter, and then it can convert from the list type to a new type. Does that answer your question? So we can have multiple type parameters if our application follows. Yes.
So, quick question on the lecture question. Is that code for example, writing it? It says to write it in data structures dot list node, so week 11 dot list node.
Oh, no. Yeah, it should be, sorry about that. That should be week 11. It was in a data structures package last semester. I did some cut and paste and didn't update this. Oh, we're actually at the last slide anyway. Hey, since we're doing live coding regardless, might as well show this. Oops. I think I showed this one other time, but so I'm going to go onto my server here. I never pushed. Oh man, going down a bad path here. So I pushed that to my repo, updated slides, poll, give my credentials, restart the server, and we should have. I'm not gonna get that dangerous and start clicking through, but we should have the updated slides on the course website. Which does bring us back to the lecture question. So how do we write reduce that takes two inputs, returns an input, and combines it a whole list into a single value based on that function. And here the types do have to be all A for this one. So say you had a function that takes two values of type A and returns a value of type B. What happens when your list is of size 1? How do you handle that one? Is a tricky question to answer. So we have the same types here for reduce. Okay, let's do some live coding. Do we have to specify what BOB is? If it can be inferred by the function that you give it, then you don't have to specify what B is. All right, so let's do some coding. And there's a few things I want to set up first. So some of the comments were when you show code in lecture, you have it all, it's all finished and everything, then you just scroll through real quick and explain it. So I want to start with a blank sheet here, blank slate, and talk about what is happening with live coding. And I used to do this all the time. I haven't done it once this semester yet, so let's change that. Let's do this. And I want to set up something first. I want to do a few different things during this where we're going to compare some runtimes. So the very first thing I want to do is just an example of passing a function, another example of passing a function. I want to do, we'll call it time function. Takes in a function with no parameters and return type unit. I'm going to return unit. Oh boy. I gotta name that. It's important that we name our variables. So it takes in a function with no parameters and return type unit. This method itself is going to have return type unit. And what I want to do is call the function that's inputted here and print out just how long it took to run that function. So first, I'm going to grab the start time. I'm going to compute the total time. And one warning that I give, not necessarily a warning, but when I do code, and especially when I'll do live coding, you'll see this, is I don't always code in order. I code in order of the thought, like what each task I'm going to do. I almost never code in order of the actual lines of code. So I know I want to sandwich the code. I mean, I guess I can do it in this case because it's only going to be the function call. But I want to think of, okay, I got to set up my timing. That's going to be before and after what I'm timing. And then what I'm timing is this function call itself. So let me get the total time. Let's see if I can get the right number of zeros. Or should I just leave this as nano time? Let's leave it in nanoseconds. Put a space there so we don't mistake. So this is going to determine, just going to print out, call the function, print out how many nanoseconds it took to run that. You know, I don't like this. I want to do milliseconds instead. I like nanos when we're updating a game every frame. If we're using milliseconds in that, and we're losing almost a full, it's going to have some truncation there. We're losing almost a full millisecond on each frame. We're going to start having some time dilation. Things are going to get weird. So I like using nanos there. Here, we only need milliseconds, so let's use milliseconds. So now that that's set up, let's do just to make sure we know how the lecture question is working. Let's do a quick example of reduce. I'm going to use the built-in Scala list for the only reason, just to show you that this is something real that we're making. This is reduce. You're seeing how to write reduce based on our linked list node that we built. But this is something that you can use out there in the wild. You can use this anywhere you want. It is something built into most languages, really. So let's create a list. Get a random list. This is something I'm going to want later anyway. List. We have a request to live code genetic algorithm. If there's time, I'll do it at the end. What am I doing here? Var, let's call it L. And I'll just work with ints today, just to keep things a little simple. Int list. I'm purposely going to do this, don't cringe quite yet, I'm going to purposely do this very poorly, just to show off something. So random list. Let me take in the size n for L colon equals math random times 100. Oh, that wasn't supposed to go there. Live coding is always very stressful, if you're wondering. Take the floor of that and return L. So I just want to be able to get random lists of size n. I purposely wrote that really horribly. That's why I want the timing code to show a few different things of why that's so horrible. So if you don't know why that code's horrible, don't worry. I will get to that part. Yes.
Are you using Java's math?
Yes.
Okay, just curious about how we got Scala. Just
Scala just uses Java's math, I believe. Yeah, it's auto-imported. Yeah, so this is actually the math library from Java. This is what Scala, I don't believe Scala has its own math library. I believe it just uses Java's.
It's lowercase math, Scala.
Lowercase? Oh. Actually, I didn't know that. Which uses Java's constants, Java's random, Java's I guess either way we look at it, we're using Java stuff. But that's a good point to make. So since Scala runs on the JVM, Java and Scala are interoperable. That you can use code from either language in programs of either type, as long as it's already compiled. They both compile down to Java bytecode. So if you have compiled code in either language, you can use it in either one. The standard library is all compiled, so we're using the Java standard library. We can use that for days, which is why you have to have both Java and your JDK and your SDK both installed. You have a Java version and a Scala version that you picked, that you have it set up in your IDE. It's because we're using a lot of Java in our Scala. So if you're worried, why don't we use Java? Java's a lot more popular out there. A lot of times you are actually using Java when you're using Scala. Just the syntax is a little different. If you want to transfer everything you know about Scala over to Java, it doesn't take incredibly long to learn the little syntactical differences, which in my opinion are annoying. Java is one of those languages where you have to have a semicolon at the end of every line. If you don't, your code breaks. So little things like that you got to worry about. It doesn't have type inference, so you always have to specify your types. There are things like that. They'll take you a little bit to get used to, but it's all mostly just extra typing that you have to add to your programs. But if you're worried about, oh, I wish this was Java because it's more useful, you could probably pick up Java and transfer all these skills over in probably a weekend, to be honest. just going through a few Java tutorials. All right, but we're getting a little off track here. So let's create a list. Numbers, I guess, equals random list of 100. Numbers dot reduce. Forgot my S again. Reduce. List of int would be helpful there. Dot reduce. Let's just do A plus B. So this is an application that we would the littlest things, when you know over 100 people are watching, the littlest things can really stump you sometimes. The order of the type and the variable name. Come on. Result equals. Then I'm just going to print the result. Oh, yeah, it wants me to. IDEs are so powerful these days. It's like, we already have a method for that. It's called sum. Why don't you just use that? I don't want to use sum because I'm showing how this thing works. So let's call time function of reduce example. Common mistake in functional programming, in first order functions, that I'm probably going to see a lot in office hours, and the T's will see a lot in office hours, is this right here. So I want to pass a function as an argument to this method, actually a method to a method in this case. Don't add the parentheses at the end. The parentheses means call this function, call this method. That's what we've been doing for a semester and a half of computer science of your education. We would always call the thing, with a few exceptions. We would always call it here, no parentheses, because we want to pass the method itself. We don't want to call it and then pass the return value. We want to pass the method itself. I guess we went through that in 115 as well. In the sorting, you probably already made those mistakes enough to learn that lesson. But we want to pass the method itself. So let's finally run this thing. This has to be an object. Oh, yeah. That's supposed to be this thing. Right? I'll get it one of these tries. Actually forgot how to do it the bad way. I always do it the other way. All right, well, let's just do it this way, because I was fixing the wrong problem. Did those just happen to be almost the same number? Oh. All right, so we got our random list. We called reduce on it to get the sum of all those values. I'm not going to sum them up. I'm just going to trust that this is the actual sum of all of these values here. Then the timing actually took about that long. About the same as our sum, which is just weird, right? Yeah, there we go. We get a bit different value there. Okay, so we have our setup. We can call reduce, but now we can do reduce with any function here. So I mentioned we could get the max value out of this list just by passing max we get the max value, min, almost no change to our code. We don't have to worry about how to initialize our accumulators or any of that. We're just going to pass a different function and have that function be the application of our accumulator. And we'll just go through the whole list, run through it, using that function to be able to get the output value. So this is an example of abstracting out what functionality really needs to change for each call of this and the actual algorithm. Similar to what we did for sorting, the sorting algorithm, most of that's going to be the same no matter what we're sorting, no matter how we're sorting it. We just need to give it a comparator. We're taking that same idea here, that accumulator pattern. There was, when we did different applications in 115, there really wasn't all that much different structurally for that pattern. The big thing is, okay, how are we combining two values? And reduce abstracts out everything else. Reduce takes everything else as the structure and then says, just tell me how I'm combining two values. Once you tell me that, I'll take care of the rest. I'll set up your accumulator variables, initialize it, and all that. I'll take care of that. Just tell me, how do I take two of your values of this type and combine them into one value of this type? If you tell me that, I'll be good for the rest. All right, so I mentioned this is awful, and that's what I was, my only problem was I had a double that I needed an int. I was trying to add a double. I was trying to add this double to a list of ints. I had to call int value. I just forgot to call my int value. This is something we usually don't want to do unless we're just coming up with random integers. And there's a better thing to call. I think I should use the random class. I'm not going down that road right now. But the part that's horrible here is this, which I almost forgot the syntax for because I don't use this. It's a horrible thing to use. But let me explain why this is horrible. And it's related to your lecture question from Monday. So this is going to append, this is the append function. It says append this value to the end of this list. For your lecture question, to write append, the first thing you have to do is iterate over this entire list, find the last element, and then append to the end of that list. So for every time you call this, you have to traverse the entire list and then add to the end of it. This is opposed to prepend, which is a very efficient operation where, well, you already have a reference to the head, just add one node before and have it point to the head. Done. Very simple, very quick operation. So, for example, if we increase this, let's actually get rid of some stuff here. Reduce, we know is going to be efficient. Well, let's just create a random list of size 10. That's where all of our runtime is coming from, which is actually surprising that it's that high. It shouldn't be that bad. Yeah, I have some extra overhead here. I don't think that's my overhead, though. It's not my overhead. I don't even know where that's coming from. But let's crank this up a bit. Let's just create a random list of size 10,000 and see how long this is going to take. So that took a full second. So even if we have 0.3 seconds of overhead, we still have 0.7 seconds just to create a list of size 10,000. It shouldn't take that long. So there's one thing we can do worth mentioning here, and I noticed it when I was looking through the list code in Scala. Scala actually is storing a reference to the end of the linked list too. So if I want to append to the list, why don't I just take that reference to the last node and just add to the end of it? And this is where we get into something more specific to Scala and very related to functional programming. Something I mentioned a few times is that Scala lists are immutable. Once you create a Scala list, You cannot change that list ever. It cannot change. There is a mutable version of the list, a list buffer. Some of you use that in your assignments, and that's fine. We're not too concerned about efficiency in 116. In 250, you will be. But if you want to use that in this class, fine, go for it. But the list class itself, the list class is immutable. It cannot ever change. So if I'm appending to the end of the, and the reason for that is if some function here has a reference to this list, and some function over here, or method, takes that list as a parameter, I don't want this function or method over here modifying my list and messing up what I'm doing over here. So Scala says, let's make it immutable so that can't happen. Now when we have concurrency, we have multi-threading, we have a distributed system across a whole server room running all kinds of computations all at the same time. No matter what we're doing, how high we scale, which Scala comes from the word scalability, no matter how high we scale, we're never going to have that problem. So let's just say you can't change the list. Now nobody has to worry about their data structures changing from underneath them. So if I append to the end of a linked list, I have to create an entirely new linked list to make sure that I don't mess with anyone who has a reference to the head of this list. So when I do this, I'm not just creating a list of size 10,000. I'm creating 10,000 lists with a total runtime, and copying over those lists every time, with a total runtime of order n squared and space of n squared. It's a lot of inefficiency. If I make one little change here, actually I think I have to reorder things. Will it let me do that? If I make one little change here and change the append to prepend, we don't have that problem. So why is this? Well, how come I can prepend efficiently but append very inefficiently? And when you're working with linked lists in Scala, list class in Scala, linked lists in general, any immutable linked list in general, prepend is always a very cheap, easy operation. You can prepend for days and not worry about affecting other code without worrying about blowing up your runtime and efficiency. But append is very bad, very expensive operation. So when we prepend, and this we should be able to crank this up. Let's go up to, I don't know, 10 million. Still took 1.2 seconds. If we change that to 10 million and have append, it'll probably take till, I don't know, a while, minutes at least. But append is very simple. So why is this? So say somebody has a reference to a list, reference to the head of the list, and it's an immutable list that cannot change, and I want to prepend to the beginning of that list. Well, to prepend, I'm going to create a brand new linked list node and have it point to the head of the old linked list. And I'm going to return a reference to this node, this new node that I created. That's the new linked list with that value prepended to the beginning of it. And then I return that reference to that head to whoever prepended to this list, and then that's it. So this other person, somewhere else in my code, I had a reference to the old linked list, the head of the old linked list. That code does not even care that there's a new node that refers to that head. It just doesn't care. It's just going to continue referring to this head, this node of the linked list, as though nothing happened, because it has no references to what happened here. What happened here didn't affect anything here. So it's just going to still have a reference to that same node and pretend that that element was never prepended. So now we actually have one linked list with 10 million elements and just references to every single node. So we can have people referring to this list in 10 million different ways and pretend that it's 10 million different lists without affecting each other. We can still have that list be immutable. It just doesn't matter because we're prepending to the beginning and not actually changing anything. But if I append to the end, I just messed everybody up because they are referring. There is a node in their linked list that does refer to that is going to jam them up. So Scala has to create a new list and copy the list every single time, just so it doesn't jam everybody up. But prepend, very cheap operation, very easy, and doesn't mess with the immutability of a list. So whenever you're working with these linked lists, always think, can I prepend here? If I can prepend, and when I do that, be efficient. And we didn't really get too many requests, but we got some good stuff in there. With that, I'll see everyone Friday. We'll talk about stacks and queues.